How's everyone doing today? Doing pretty good, doing pretty good. Can't complain. Two exams this month, but none in April. Let me see. Are they not equally spaced? It's probably just yeah, that's just how it works out because because of the way the material is laid out. So so we have an exam over at the beginning, sort of over over sort of the vector stuff, and then vector functions, and then we talk about functions of two variables, and then or 2 and 3 variables, and then we cover like the derivative stuff, and then that's one exam. And then we have the integration stuff, and that is one exam. And then sort of everything after that is sort of the integration theorems, surface integrals, line integrals, that kind of thing. So it's kind of sticking the stuff that sort of goes together and putting it in a single exam. Yeah, exam 4 is the final. Yeah, exactly. Yeah, so the next week, next exam is next in a week and a day, next Tuesday. Final is cumulative this semester. Yeah, that's how it was in previous semesters, except for literally last semester was the only time we didn't have a cumulative final exam. But the final is indeed cumulative, but it's weighted heavily towards newer material. Yeah, I think it's usually like, I forget. It might be different now, but I think it's usually like 40%-ish newer material, or 60%. I don't remember exactly. I'd have to check, but yeah, it's weighted more towards the newer stuff, and then it hits like the greatest hits from like previous exams. Yeah, but it is indeed cumulative. Yeah. Okay, so we're gonna finish up talking about polar integration in polar coordinates, and then we will look at integration in cylindrical coordinates today. Okay. So we saw with polar coordinates, instead of using x and y in the plane, so polar coordinates are two-dimensional, instead of using rectangular coordinates, where we look at how far along the x-axis, how far along the y-axis we go, we identify a point using r and theta, where r is distance to the origin, and theta is the angle measured counterclockwise from the positive x-axis. And we had the important relationships. X is our cos theta, y is r sine theta. And from that, you can derive x squared plus y squared is r squared. But it's good to have just sort of sitting there on the top of your head, because we use it often. Okay. So we looked at polar rectangles, how to integrate over those. And polar rectangles are basically going to be r lies between a number and a number, theta lies between a number and a number. And those are going to be regions bounded by circles centered at the origin and lines through the origin. But we can integrate over somewhat more general regions. Suppose we have a region where r lies between one function of theta, r1 of theta, and another function of theta, r2 of theta. And theta lies between, say, theta 1 and theta 2. So instead of having r lie between two numbers and theta lying between two numbers, now we have r lying between functions of theta and theta lying between numbers. We don't ever do theta lying between functions of r, because that's not something that's nice to deal with, really. We'll call this region D. So suppose this is like theta 1. This is theta 2. And suppose this is say this is r1 of theta, and this is r2 of theta. Suppose that's our region D. Okay, so the way we integrate over this is exactly the same way. So we have a function of x and y. Then we're integrating over a region that we can describe in this way with respect to area. The way we do that is same way we always do. So first, we switch to polar coordinates. So x, everywhere we see x in our function, we replace with our cos theta. Everywhere we see y, we replace with r sine theta. R goes from, so we always integrate with respect to the variable bounded by functions first. So r goes from r1 of theta up to r2 of theta. Theta goes from theta 1 to theta 2. And what do we say dA is? In polar. You need to remember this. What is dA in polar? Anyone remember? Right, r dr d theta. So r times dr d theta. All right, so you need to multiply the function, the whole thing, by r. So that's how we integrate over a more general region where r is bounded by functions. Exact same thing we do for polar rectangles, except r is bounded by functions now, but exactly the same thing. Okay, so let's look at an example of this. R squared cos theta. It would. It would, Nick. It would, because what this means is this means everywhere you see x, you're replacing with r cos theta. Everywhere you see y, you're replacing with r sine theta. What you're saying is everywhere you're seeing x replaced with r squared cos theta, everywhere you're seeing y replaced with r squared sine theta, and that means something different. So if you had like x squared, right, that would become r cos theta, and then you multiply by the r dr d theta, right, and then it ended up being r cubed cos squared theta. You do, but that's not the way you want to write it. Is all I'm saying. I think you have the right idea. I think you have the right idea, but yeah. But writing it like that would mean something different. A fixed form of so it depends on whether you're integrating on in rectangular or polar. So if you decide the region you're integrating over is described best in polar, you would switch to polar coordinates, and then your dA would become r d theta. If you decide it's best described in rectangular coordinates, and say it's like vertically simple, right? Then you integrate with respect to y first, and then with respect to x, and then dA is dy dx. And then if it's horizontally simple, you do dx dy. But yeah. Okay, so let's do an example of this. So let's find the area of the region already. Okay, so the area of the region inside the circle x squared plus y squared equals 2x. So that's going to look a little weird. That is indeed a circle, as we'll see. But there's a reason I'm writing it like that. And outside the circle, x squared plus y squared equals 1. Okay, so let's make a quick sketch. It's usually a good thing to do. Okay. So first of all, let's figure out what this, how to sketch this circle, what the center is, what the radius is. X squared plus y squared equals 2x. So we're going to write it in the standard form. X minus a squared plus y minus b squared equals r squared, or the radius squared rather. So let's bring the 2x over. Okay, so x squared minus 2x, what do I need to add to that to make a perfect square? Right, I need to add 1. So adding 1 to that, and then I need to add 1 to the other side as well to keep the equation, right? What you do to one side, you have to do to the other side. And then that, of course, is x minus 1 quantity squared plus y squared equals 1. Okay, so we have writing it in this form tells us what the center is and what the radius is. What's the center of that circle? it's 1, 0, right? And the radius, of course, is square root of the right-hand side, which is 1. Okay, so that's a circle centered at 1, 0 of radius 1. So that is this guy. So it's going to go through the origin. That is kind of hideous, but pretend that one goes through the origin, right? Because the origin is distance 1 away from the center, 1, 0. So you want everything inside of there, and outside of the circle, x squared plus y squared equals 1, just the unit circle centered at the origin. Right, so the region we're talking about is this region here. We want the region inside the circle centered at 1, 0, outside the circle centered at the origin. Does everyone see that's our region? Okay. So what we need to do is we need to describe this in polar coordinates. Because basically always, if you have a region in the plane bounded by circles, it's almost always easiest to do that integral in polar. Okay. But first of all, let's figure out what we'll call this region D. Let's figure out what the integral that we need to do is. So if you want to find the area of a region D in the plane, what function do you need to integrate over that area? So this is something you need to know. So if you want to find the area of a region D, then you integrate 1 over that area. You just integrate the constant function 1. Right? In other words, you don't even need to write the 1. It's just, yeah, the integral of 1 dA over the region D. Okay, so that's the integral. Let's figure out the bounds of D and then convert to polar. Okay. So, all right. So let's find the bounds on R. Okay, so here I sort of mentioned this before, but I didn't use explicitly this. But here's how I like to think of finding the bounds for R, right? So draw a line starting at the origin through your region D. So draw a straight line through the origin through your region D. Here's how we're going to decide R. So remember, R is a distance from the origin. So look at what is the first thing. So start at the origin, move out. What is the first thing? What is the curve that this line first hits? We need to write that in polar coordinates. So the first thing we hit is the piece of the circle centered at the origin. Does everyone see that's the first thing the line hits as we move out from the origin, as R is increasing? So how do we write the circle x squared plus y squared equals 1 in polar coordinates? So let me write this out. So line from the origin. First hits the circle, x squared plus y squared equals 1. That's the first boundary of our region we hit. In polar, what is x squared plus y squared equals 1? Well, you can just convert directly to polar. X squared plus y squared is r squared in polar. And we basically just always assume r is positive for the most part. But that's the set of points of distance 1 from the origin, right? So all of those points, the r coordinate is going to be 1. So we need to write each curve as r equals something. So the first curve we hit is the circle x squared plus y squared equals 1. That's r equals 1. The second curve we hit the outer boundary is going to be this other circle. This guy here. So that's going to be the upper boundary for r. So then it hits the circle x squared plus y squared equals 2x. And there's a reason I wrote it like that. So we're going to turn this into polar. So just rewrite both sides of the equation in polar. X squared plus y squared, remember, as r squared. And what is 2x in polar? It's 2r cos theta. And we need to write this as r equals something. So just divide both sides by r. So we get r is equal to 2 cos theta is the equation of the second circle in polar. The upper bound. So then we have bounds for r. So r is bounded below by r equals 1, so by 1, and above by 2 cos theta. I didn't take the square root. I divided both sides by r. So r squared is equal to 2r cos theta. Divide both sides by r. R is equal to 2 cos theta. Yeah. Okay. So now we need to get the bounds for theta. Okay, so this is the one that kind of trips a lot of people up. So let's look at that. Okay, so we're basically going from, oh, come on, dude. There we go. We're basically going from here up to here. Right, so the least angle we make with the positive x-axis is down here at the meeting point, and the biggest angle we make is up here at the meeting point of the two circles. Does everyone see that? This angle, this interval of angles here between those two guys is are the bounds for theta. So we need to find what the lower one is and the upper one is. And those are going to happen where the two circles meet. So we're going to find where the circles intersect. We're going to switch to polar. And we're going to find the angles theta where that happens. Okay, so we're going to write the two equations of the circles in polar. Well, one of them is r equals 1. And the other is r equals 2 cos theta. So we're going to set the two equal to each other. Oops, hang on. This is going to be where the two intersect. So we have 1 equals 2 cos theta. Right, both of these are equal to r, so we're setting them equal to each other. So we have cos theta equals 1/2. We need to figure out a value of theta. Okay, so there are two values where cos theta is equal to 1/2, right? One of them is going to be the lower one of them is going to be the upper one. What's the lower one? Let's say where theta is negative. So cos of what is 1/2? So pi over 3 and also negative pi over 3. And we're going to take it to be negative because we want to start at the bottom one and go up to the upper one. So we need an interval starting with the lower one up to the upper one. And it's easiest just to do negative pi over 3 up to pi over 3. If you wanted to say like 5 pi over 3, then you have to do 5 pi over 3 to 7 pi over 3, which is less natural. How we got the r for x squared plus y squared equals 2x? Yeah, so there's a reason we wrote it in that form. And that's because it's easier to get the formula there. So x squared plus y squared equals 2x. If you want to convert to polar, you just make the substitution. X squared plus y squared is r squared, and then 2x is 2r cos theta. So we have r squared equals 2r cos theta, but we want to get this as r equals something because we're finding bounds for r. And so we could just divide both sides by r, and we get r is equal to 2 cos theta. Does that make sense? Still confused? Okay, all right. Okay, okay, so we got our bounds for theta, right? So we have negative pi over 3 down here, pi over 3 up here. Our interval for theta is from negative pi over 3 up to pi over 3. Those are our bounds for theta. Okay, So let me rewrite those. So r, we said, goes from 1 up to 2 cos theta. Theta goes from negative pi over 3 up to pi over 3. So that's our region D. And we want to integrate just the function 1 over there. So let's switch to polar. So we go to our function. Everywhere we see x, we replace with our cos theta. Where we see y, we replace with our sine theta. Well, our function's just 1. dA, we said, becomes r dr d theta. And then r goes from 1 up to 2 cos theta. And theta goes from negative pi over 3 up to pi over 3. And so let's integrate. OK, doing our inner integral. So distribute the r through. We're just integrating r with respect to r. R becomes 1/2 r squared. Evaluated from r equals 1 up to 2 cos theta. So we got 1/2. 2 cos theta quantity squared is 4 cos squared theta. And minus 1 squared, which is 1. So we get integral from negative pi over 3 to pi over 3 of, let's distribute through the 1/2, 2 cos squared theta minus 1/2 d theta. OK, so this is going to be a very useful thing to know. Sorry, this example is taking a lot longer than I intended. So often when we do polar, and as we'll see, also cylindrical and sometimes spherical, when we do these integrals, we'll be integrating cos squared or sine squared sometimes. And there's a way to rewrite that to make it easier to integrate. So I would have these memorized because they're going to make your life a lot easier. So cos squared theta is going to be equal to 1/2 1 plus cos of 2 theta. So these are the double angle formulas here. And sine squared theta is similar, except it's 1/2 1 minus cos 2 theta. Those are good to have memorized. OK. So let's rewrite this using that, and then we'll be able to integrate directly from that. So 2 times cos squared theta is going to be 2 times 1/2 1 plus cos 2 theta, which is just 1 plus cos 2 theta. The 2 and the 1/2 are canceling. And so let's rewrite is it doing this today? Our integral negative pi over 3 to pi over 3. Okay, so then we get 1 plus cos 2 theta minus 1/2. So cos 2 theta, and then 1 minus 1/2 is 1/2. So cos 2 theta, when we integrate, becomes 1/2 sine 2 theta. 1/2 becomes theta over 2. And we're evaluating this from negative pi over 3 to pi over 3. And so sine of 2 pi over 3 is going to be root 3 over 2. Sine of negative 2 pi over 3 is going to be negative root 3 over 2. So we get root 3 over 2 from that first one. Oh my goodness, it looks exactly the same. And then for the pi over 2, we just get pi over 6 minus negative pi over 6, which is pi over 3.
Okay, Professor, I just got really confused. How did we go from the 1/2 for cosine squared theta minus 1 back up to that arrow and then come back down? What happened right there?
Oh, so this here is our inner. So do you get how we got there?
Right. Yeah.
So then I just distributed the 1/2 through. And so I got the 2 cos squared theta minus 1/2. And I plug that into the outer integral. But we have the cos squared theta bit, which we don't know how to integrate as is. But if we use these double angle formulas down here, then we can rewrite it in terms of something that we can integrate. And those double angle formulas are good to know. So the 2 cos squared theta becomes 2 times 1/2 1 plus cos 2 theta. And then the 2 and the 1/2 cancel, and you just get 1 plus cos 2 theta. So then it's 1 plus cos 2 theta minus 1/2, which is cos 2 theta plus 1/2. The 1 minus 1/2 is 1/2. Like I don't want to spend too long on the evaluation. The important bit of the evaluation here is using these double angle formulas down here, which are very good to know because those pop up all the time. You get sine squareds and cos squareds all the time that you have to integrate. But yeah.
Okay, thank you.
All right. So any questions about that one? For these ones, it's a little more complicated. But to find the bounds for R, I like to do the line through the origin thing. And then see the first curve you hit, write that as R equals something, that's a lower bound. The second curve you hit, write that as R equals something, that's the upper bound. And then the bounds for theta, sometimes you have to think a little bit more about what's happening. But usually it's going to be at the intersection of your R bounds. Okay. So that took approximately half an hour longer than I hoped. But let's start talking about cylindrical coordinates. But yeah, so just sort of to emphasize, polar coordinates are just like an alternate, a different coordinate system that make it easy to describe regions bounded by circles and lines through the origin, right? So like sectors of annuluses and then other stuff bounded by circles, basically. Those are not so easy to integrate in rectangular coordinates, but they're very easy in polar coordinates. So if you see stuff bounded by circles, you should, in the plane, you should switch to polar coordinates and integrate that way. That's essentially what they exist for, because it makes life easier that way. Okay, so cylindrical coordinates are similar, but now this is for R3. Okay, so cylindrical coordinates, so remember rectangular coordinates are going to be where we use x, y, z. Cylindrical coordinates, the coordinates are going to be r, theta, and z instead of x, y, and z. And luckily, we already know what r and theta are. They're going to be the same as from polar coordinates. So here's how this works. So here's our point x, y, z. Z is the same z from there. Z is exactly the same there. And r and theta are the same as they are in polar. So what you do is you project down to the xy plane. So you keep x and y the same, but you take z down to 0, down to the xy plane. And then let me actually hang on. This is probably better this way. So then r is going to be the distance from the origin of the projection. And theta is going to be the angle measured counterclockwise from the positive x-axis. So we projected the xy plane. R is going to be same as in polar. So just so we don't get this mixed up with spherical, if you're not projecting down to the xy plane, here's sort of how you think of it. R is going to be the distance of your point to the z-axis, right? So the distance to the z-axis, not the distance to the origin, which is the same as if you project this down to the xy plane and then look at the distance to the origin. And theta, I like to think as theta. So think of a plane going through, half plane going through the origin. Or like going through the z-axis. So I like to think of the positive x-axis as being theta equals 0, and then rotating around counterclockwise. So think of that as like the angle about the z-axis. And let me say measured counterclockwise. Or let me just say counterclockwise. From the positive x-axis. So points that lie on or above or below the positive x-axis are going to be theta equals 0. Because when you project them to the xy plane, they lie on the x-axis where theta is equal to 0. And then think of increasing theta as going around the z-axis counterclockwise. Or you could just project to the xy plane, and then the angle theta there is the same as in polar coordinates. Okay, so cylindrical coordinates are going to be useful for integrating over three-dimensional regions, which are bounded by cylinders, planes, and sometimes cones. So we're going to use them for regions in space. So in R3. Bounded by cylinders, hence the name. Cylinders, planes, and cones. So let's look at a few regions in R3, or let's look at the equations of some of these guys in R3 really quickly. So the cylinder, right. So just a reminder. So this is what you need to remember. In cylindrical, x is our cos theta, y is our sine theta, z is z, of course, but we still have the x squared plus y squared is r squared relationship too. Okay, so let's look at the cylinder, say x squared plus y squared equals 4. Right, so that's a circular cylinder about the positive z-axis of radius 2. So let's write this in cylindrical, right? So x squared plus y squared is r squared. And since we're always taking r to be positive, the equation of this cylinder in cylindrical is r equals 2. That's the equation of the cylinder, x squared plus y squared equals 4, right? It's a set of all points whose distance from the z-axis is 2, right? And remember, r gives you distance from the z-axis. Or alternately, if you project down to the xy plane, it lies, whoa, that's kind of ugly there, but it lies on the circle of distance 2 from the origin. So cylinders are going to be r equals, yeah, it's centered on the z-axis, correct. Cylinders are going to be r equals something. So similarly, if we have, not as important, but theta is equal to some constant, those are going to be half planes where all the points make angle theta with the positive x-axis, or theta naught. So suppose this is angle theta naught here. Well, if we look at all such points, that's going to be a half plane. Imagine it extending infinitely and away from the z-axis in that direction. Oops. So that's a half plane. Theta equals a constant. So r equals a constant is a cylinder. Whoops. Theta equals a constant is a half plane. And then let's look at half cylinders here. Yeah, let's do that. Suppose we have z equals square root x squared plus y squared. So if we had z squared equals x squared plus y squared, that would be a full cylinder. It would include the top half and the bottom half. If we take the square root of both sides, positive square root x squared plus y squared is the top half, negative is the bottom half. So usually we're just taking half at a time. So the top half is going to be a cone, a half cone. And if we convert this to cylindrical coordinates, z stays z. What is square root x squared plus y squared in cylindrical? So x squared plus y squared is r squared. Square root r squared is just r. Exactly. So z equals r is what the equation of cones look like there. Well, z equals r is one example of a cone. You could have like 2x squared plus 2y squared, and that would be z equals root 2r, etc. But yeah, so cylinders are just r is equal to a constant. And then cones are going to be z equals a constant times r, essentially, half cones. OK, so we'll leave it there. We'll look at how we integrate in cylindrical coordinates next time. But yeah, any other questions?
I had a question from earlier on in the lecture. So it was about the part in the example problem where it said, find where the circle intersects in polar.
Yeah.
I was just confused how like we did that first step there where it says like 1 equals 2 cosine theta.
Right. So we look at the equations of the circles in polar. We converted those already when we found the bounds for r. So we saw the circle centered at the origin was r equals 1. The circle centered at 1, 0 was r equals 2 cos theta. So the intersection of those two, they're both r equals something. So at the intersection, the r's are going to be the same. So that we just set the right-hand sides equal to each other. So r equals 1, r equals 2 cos theta. So we set 1 equal to 2 cos theta. And then find the values of theta that satisfy that.
Okay, so essentially you can just set like both of the like radii equal to each other.
Right, so because we wrote both as r equals something, and at the intersection, that's where your two things are going to share points. So the r coordinates are going to be the same at the intersections. And since we have r equals something, we could just set the right-hand sides equal to each other since the left-hand sides are already equal.
Okay, thank you.
If that makes sense. Yeah.
Also, I was able to figure out my question. Sorry, my mic was broken.
All right, that's good. No problem. All right, so I'm going over to the office hours soon,
Okay.
if you need to see me. But
hey, thank you.
Have a good one, guys.